Hi everybody, good morning. And I will start the presentation with a small question. For the people who are used to the Bucharest traffic, I have a question if they really like it, because personally I hate it. There's a big hype right now with autonomous cars and self-driving cars. They say that they will resolve everything, but all the traffic problems or the infrastructure problems, they will talk with the infrastructure and no more traffic jams. But what happens if a self-driving car is hacked? Let's see. I'm accompanied by my colleague, Gabi. He's our lead researcher in the cybersecurity field. My name is Mihai. I'm a senior software engineer, embedded engineer. And today we will be trying to explain a mechanism of stopping intruders on the canvas. We have just a few bullets on our agenda. The last one is quite technical. The first three I will be presenting, and the last one will be covered by Gabi. We'll present our company, a few automotive cyber hacks, and the CAN bus, the most used bus in the automotive domain. So Garrett started as a turboprop company. They built engines and aircraft engines. It was initially named Garrett AI Research, and AI did not stand that in 1950s for artificial intelligence. These are the three main pillars of our company. The majority, the biggest part is the turbocharger part, the turbocharger industry that we figure. We have a very big factory here in Romania and one big R&D center in Pipera. The rest of the two, we build also hybrid electric powertrains, and we have another division specializing in cybersecurity and usually things that go on and live in the vehicle's electrical system. It's called connected vehicles, and we are part, I hope my pointer works so you can see it. You can't probably. Here, cybersecurity. Okay. So this is Garrett in terms of figures. It's a quite relatively small company given the revenue, and it's quite, if you compute the capita per employee, it's quite bigger than in some semiconductor, quite bigger than in the semiconductor industry. Okay. So given the fact that the cars right now are quite complicated. One big example is Tesla. They have a lot of computers inside the car. They use a lot of various buses to communicate between the computers. Ethernet, CAN, MOST, LIN, FlexRay, whatever you name it. And this leaves room to hacking. This is quite a typical new generation car architecture, in which you have Bluetooth, Wi-Fi, VLAN, keyless entry, tire pressure monitoring. Everything that's wireless is a big issue because these are attack vectors. So this is a way of, or a mechanism or an entry point for a hacker to get into your car. Personally, when I did the research, I was expecting that the OBD port, it's a diagnosis port in your car. This should be in my opinion, this was the major attack vector, but it wasn't, because if you want to go and use the OBD port, you need to get into the car. So this is a problem. You need to open it. The most common issue, and it's quite interesting and funny, okay, because the data server. So given the fact that the cars have an internet connection, it's quite easy for anybody to access it if you know some IP addresses, some servers, and you can access it. Another entry point into the car is the keyless entry, because this is quite a funny thing, because some guys in the UK use the software-defined radio and two antennas to connect to the key fob and connect to the car, and they simply open the car. The owner was in his house, he was one of the team, and when he was sleeping, they just opened the car and entered. Okay. So these are from 2015, these are the major hacking big problems that appeared in the industry. 5 of them are related, and the funny thing is that the provider for that issue was based in Bucharest. And that's about it, about that producer. So BMW had a problem with its infotainment system. 2.2 million cars were affected, so they communicated with their servers with an HTTP connection which was not encrypted on port 8080. The Fiat issue, I will explain it in a separate slide, but it's also related to the infotainment. The idea is that the infotainment is usually linked and connected to one of the CAN buses because it needs to read, for example, fuel consumption, speed, average speed, statistics like that. The Nissan Leaf, also a similar issue. The infotainment had a problem. The hackers they managed to enter the car, control the steering wheel because the car had, being an electric car, they had a self-parking option on it, and they could control almost everything, braking, acceleration, steering wheel, everything. Volkswagen also had IVI, stands for in-vehicle infotainment, next to the Volkswagen badge there. They had also a similar issue, another HTTP connection with no encryption. Everybody said that the fact that the OpenSSL was not automotive grade ready as a software, and they said that, okay, this is one of the issues. For both Tesla hacks, they found a lot of vulnerabilities given the fact that they have so many computers in them. There is not so much information on the market and about the 2 Tesla hacks, but again, Hyundai's Blue Link was also a similar issue. The Blue Link had a connection between your mobile phone and the car. This one had also HTTP connection, and it was a telnet over HTTP on port 8080, so not encrypted. Cadillac had also a small issue on the CAN port, given the fact that the CAN, which was exported to everybody, the one on the OBD port, was directly connected to the rest of the other CANs with no gateway protection. So, if you can see here, I think 5 of them, or 6 of them, 6 of the big OEMs here had issues because they had the same vendor, and the vendor made a very big mistake. I don't know, maybe try to have different vendors, and I don't know, just an idea. Okay, so the Jeep hack is very interesting because it was there was a lot of publicity on the subject because two guys, Chris Miller and Charlie Miller and Chris Valasek, they talked to Wired. They made a lot of publicity on the issue. So they managed to fully control the car, almost everything. Use the steering wheel with the accelerator pedal, use the braking pedal, stop the engine when the car was driving on the highway, and again, the vulnerability appeared on the Uconnect system. So it's a platform. Uconnect is actually their application, which connected to the infotainment system, and they managed to take control over the CAN network in the car. And an interesting thing is that any connection that was, any cellular connection on the Sprint network that tried to access the car with an HTTP connection knowing the IP, it could have had a full access on it. And they crashed it. It was quite a big hype. I think you can see Wired here. They put a lot of videos, and it was cool to see how you can control from your home a steering wheel. So not in games, but in real life, Yeah. So the CAN bus. This is one of the most used interfaces in automotive, digital interfaces. It was designed and built in 1983 for Mercedes. The interesting thing is that, it's royalty free, so you can use it freely without paying any money to anybody. For example, I2C they wanted to use it, but it was, they had royalties on it. It's used in automotive, marine, elevators, tanks, boats, everything, because it has a very high tolerance to noise. I will try to explain. So if you can look at this picture here, I don't know if you can see, that's an engine, transmission, instrument cluster, doors, alarms, whatever. If each and every of the top components would have had a direct connection to the ECU or the body control module, you would have kilos of wires, a lot of, and a very expensive wiring solution, because the wiring harness is the third most expensive part in a car, if you can imagine. Not the chassis, but the wiring harness, because the labor is quite expensive on it. You need to put plugs, put whatever. So it reduces weight. It reduces cost, because almost any automotive controller, which is probably 2 or 3 rows, can have a CAN controller, maybe a CAN transceiver. It has speeds from 100 kilobits to 1 megabits, and it has also a mechanism of protecting the frames, the CAN data against errors. But Gabi will go a bit into details in a few other slides. It works well on small distances. The cars are small, and it has low impedance. This means that it can consume quite some power. Usually the CAN line has 2 wires, a CAN high, CAN low. They have some terminated resistors, 120 ohm resistors, and the transmission is done only on these 2 wires. You don't need a ground or whatever. And the funny thing is that when the CAN transceiver tries to demodulate the data, it will do a difference between CAN and high-low, CAN high and CAN low. So if you have some noise on one of the lines, noise being in both lines, do a diff, it disappears. So it's called a 2-line differential signaling interface. The voltages are from 0 to 5 volts, depending on the baud rate. Higher baud rates need bigger voltages because of the noise. Usually, normal microcontrollers don't have the transceiver, so this is the adaptation layer between the physical layer, which is the actual line, and the TTL, transistor transition logic. So if this can be, for example, 3 volts or 3.5 or 1.8 or 5 volts, and this can be, again, depending on the baud rate. So usually CAN controllers are embedded, and almost all microcontrollers have it. The transceivers, you need to buy it probably separately. So I will leave Gavi.
Thank you, Mihai. Hello, everyone. So let's talk about the security of the CAN bus. So there are some few major security problems of the CAN bus. So it's easy to tap. Once you're inside the CAN bus, you can receive all the messages. You can send any message you want on that CAN bus, and the receiver cannot validate your the message came from the legit node. So you don't have a mechanism to, let's say, to be sure that that message is valid. Anyone can send any message on the bus. And another big problem is the denial of service attack. You can do really easily a denial of service attack by simply sending a high priority message in a loop over and over again and keep the bus busy with that message. But there are some security measures. One of them is the gateway. So by gateway, you can isolate multiple subnetworks and choose which message can pass from one subnetwork to another. This way you can also isolate the TCU from ECM, the telematics unit from the engine control. So if the TCM is compromised, you cannot inject messages directly to the ECM to do stamping. Another protection measure is the private CAN. A private CAN would be a CAN that has no exposure to the outside world. Another measure, the message counter. So you put in your message a counter, and every time you send that message, you increment that counter. So if an attacker will try to send you a message, it has to have the correct counter. Okay, and the last method, the BIT Stomping, we are going to talk right now. But first, let's dive into the CAN protocol. So, this is the CAN frame. This is a capture from a scope, from a CAN frame transmission. You can see here the CAN high and CAN low wires. Both are a differential signal. You can see here the differential signal between them, and here the states. So you have the startup frame, and then you have an arbitration ID, 11 bytes. Then you have the size of the payload. Then you have the payload, and at the end here you have a CRC to validate the entire frame. So when a message is transmitted, it's considered received after all the bits are sent and the CRC is valid. And then after the CRC is validated, then the frame is sent to the upper layer. How the message is transmitted on the CAN? So let's say you have a node that wants to transmit a message. It waits for the bus to become idle. Idle means 7 recessive states in a row, 7 ones in a row. And then it starts all the nodes that want to send a message enter the arbitration process. Arbitration process means deciding which one has the most important message. This is the arbitration process. Let's say one node tries to send the message ID 123 and the other 134. So they start sending the bytes, and at this point, one is sending a 0, one is sending a 1. 0 is overwriting the 1. This one say, okay, someone is sending a 0, I'm sending a 1. Someone has a more higher ID. So this one lose the arbitration and stop transmitting the frame. Okay, this here is named the bit error, when a controller is writing 1 but reads a 0 from the bus state. Let's see how this is possible. So here we have a CAN transceiver. So it has 2 possible states. Recessive. Recessive means it's sending a 1. All the nodes on the bus are sending a 1. That part from the transceiver is disabled. So the CAN high and CAN low are derived through this 2 resistor to 2.5 volts. So the difference is 0 negated this one. Everyone will read the 1. If any of the transceiver is sending a 0, this logic is enabled. The CAN high is pulled directly to 5 volts, CAN low directly to ground. The difference is 5 volts negated is 0. So if any of the transceiver is sending a 0, everyone from the bus will read a 0. And this is the bit error. And the controller, whenever there is a bit error, during the arbitration process, the arbitration is considered lost because there's another higher priority message that need to be sent. But if the bit error happens after the arbitration process, this is considered an error and will be pushed to the upper layers. So, BIT Stomping is the technique of blocking a message using this bit error. It sounds quite simple, but there are a lot of challenges. Let's say we have this message being transmitted, and we want to make a detection and block it. We'll have to read all the data till here, and then make a detection based on the received data. And while the CRC is transmitted, we should decide whenever or not to block that message. And when it's come to end of frame or during the CRC, we can stomp any bit here, and the frame will be no longer valid. Okay, so the main challenges are that you need a custom CAN controller because a normal CAN controller will send you the frame only after it's received the end of frame and the CRC is valid. So you don't know the arbitration, the data of the frame. So you need a custom CAN controller that will push here, will push you the arbitration ID to the application, and then here DLC, here the data. So you have time to evaluate this message during the CRC field transmission. Okay, another challenge is that a CAN controller is not able to do the BIT stomping after the arbitration process, because there are some, the CAN controllers are implementing an ISO standard, and you cannot block a message. All right, and of course the high speed of the CAN bus that can be up to 1 megabytes per second. So so on a 500 kilobytes per second, you will have like 50 microseconds for the detection to give the final result and make the BIT stomping. We also made an experiment of the BIT stomping. I have created a CAN bus. I used a CAN USB device to inject messages on that CAN bus, and then using an FPGA, I implemented a custom CAN controller that can make this BIT stomping. So this FPGA was sending the data to an IDS system. The IDS system replies. So for the sake of simplicity, I just put the rules. If you see the arbitration ID 355, just block the message. And here, after the data transmission, you can see here, these 2 bits should be 1, but it was stomped to 0. And then the transmitter stops sending the frame. And here we have different levels because the sender was using here 5 volts, but this one was using just 3.5 volts. So that's the threshold. The threshold, yeah. All right, so so we can use this BIT stomping to achieve an IDPS solution, intrusion detection and protection system. So the best place to place this one is in the gateway, because in the gateway you have access to all the CAN buses from the car, but you will need this custom CAN controller to be able to read the data as it's transmitted and make the BIT stomping, and you need an IDS system that should take the decision of blocking or not. All right, the conclusion, the BIT stomping is a really promising solution for protecting the CAN bus. It requires a really high accurate IDS system that should comply with the high requirements of automotive standard in safety and security, and also needs a custom hardware to be made. Now we are open for questions.
BIT stomping doesn't seem to do anything about denial of service attacks.
You can achieve denial of service with the BIT stomping, but you don't want to block any message. You want to block just an attack message. So you need the IDS system to, let's say, to scan the message and then take the decision of blocking or not.
Yeah, I know, but let's say if I have a custom, I inject my own CAN controller and I want to do a denial of service attack, and I just send the highest priority messages on repeat.
Okay,
that was one of the main points you pointed out as attacks on the CAN network. Like, does BIT stomping do anything to prevent?
Yes, you can use BIT stomping to prevent the denial of service attack. So a CAN controller that is connected to the CAN bus is sending the messages, and if there are any errors in the transmission, inside the controller there's an error counter that gets incremented. So after 16 errors in a row, the CAN controller is disabled. This is named the bus off attack. So using the BIT stomping, you can stomp this CAN controller 16 times in a row, and then this one will go into a passive mode. And this way you can disable the CAN controller. Now if it's a custom CAN controller, like this one, and doesn't get disabled on errors, yeah, this will be a little trickier.
But you can detect it.
Yeah, you can detect it.
No?
Thank you.
Hi, thank you for the presentation. My question is, how does this impact the latency on the CAN bus? Because the CAN bus is supposed to be a high-speed network where messages it's critical for messages to arrive in very short.
Yes, of course. So we don't, so we process the message as it's transmitted. So we don't impact the speed of the CAN bus. We don't, we're not a proxy to take the message from somewhere, analyze it, and then send it to the destination bus.
But the IDS does.
Hmm?
The IDS does.
Okay,
No,
so
no, it's blocking the message on that bus. So whenever the message is transmitted, during this time, the IDS is processing the message, and here after the CRC is taking the decision of whenever this message should be blocked or not.
So you actually jam the message in its frame. So this is not another CAN messages. This is your initial message. So you simply, if you have enough computing power to compute everything until this point, you have a few bits in which you can use BIT Stomping and jam it, and that's it. And also CAN bus uses priorities, and the sender will simply retransmit it. So maybe the latency would be 1 frame. Okay, let's say 1 frame. But 1 frame compared to milliseconds in a gateway, it's almost unseeable.
Thank you.
Okay, guys, only one more question.
Okay.
So,
On the left?
Okay, so my question is to do the CAN network protection. The first one, problem to solve is to detect the attack. So, like, how do you detect the attack? By just using the payload of the packet? Because I see that you have to make a decision like very fast. You have to compute the data and make a decision, and then like block the CRC. Maybe kind of using the BIT Stomping to like describe the CRC code. So it's like very fast computing.
Yeah.
And then, so that's how do you stop the attack? But how do you detect the attack? Right.
So besides the BIT Stomping, Garrett offers a solution for a CAN IDS. It's an intrusion detection system. It's a software which is placed wherever you want it, and it uses a set of rules, and it's fine-tuned for the actual vehicle. So this CAN transceiver doesn't work by its own. It discusses with a software called IDS, in which you actually model the CAN bus there with rules, with timings for messages, with message IDs, with payload sizes, with everything. So when you decode this data, you send it to an upper layer, more intelligent software who says, okay, it's corrupt, it's an attack or whatever, jam it, and you jam it here. So it's actual feedback loop.
I will give you one quick example. So imagine that you have a cyclic message that is being transmitted every 1 second. If you see that message after 0.5 seconds, that it's being injected. Or another example, let's say you have 2 buses, and the gateway is forwarding a message from one bus to another. If you see the message just on the destination bus without any matching on the source bus, that this message should be blocked also. So we have a lot of algorithms that can detect these malicious activities.
So you already have this solution for your customer?
Yes.
Already?
Yeah.
Okay.
Yeah.
Thank you.
awesome. Thank you so much,
Thank you so
Gary and
much.
Mihai. Yeah.